Section 9.8 is on halogenation. And on halohydrin formation. So starting with halogenation, because we're gonna do both of those reactions in this section. Starting with halogenation, the generic reaction is to take an alkene and react it with a halogen molecule. This is usually done in a chlorinated solvent like CCl4 or CH2Cl2, although your textbook doesn't indicate solvent in these reactions, so we won't worry about adding that to our notes as well. And we get the halogen adding across the double bond, syn, both halogens in the same direction. This reaction can also be done with the chlorine molecule. It doesn't work with fluorine F2 because the fluorine molecule is too reactive. So I guess it does work, but it's a very exothermic reaction, explosive, and just not a good way to do that type of synthesis. So you're not going to see it with F2. With iodine, I2, it's a very slow reaction. It does work also, but it gives really poor yield. So again, not a good way to put iodines on the molecule. So you're usually just going to see this with Br2 or Cl2. Considering the three variables that we've been considering for all addition reactions, Markovnikov versus anti-Markovnikov, the stereochemistry, syn versus anti, and then rearrangement of a carbocation. For this particular reaction, Markovnikov does not apply because we don't have hydrogens at all. Just like we saw with hydrogenation, it's just two bromines. You put one on each carbon. It's pretty simple. You don't have to really think about what goes where. The reaction mechanism, which I am going to show you, doesn't really go through a carbocation intermediate, so there's no rearrangement to worry about, which is nice. It's a very simple reaction. And then last but not least, the bromines will add anti to each other. And we'll see that when we look at the mechanism. So we're going to take this pretty simple alkene to use to draw the mechanism, and I'm going to draw it with a chlorine molecule because your book uses bromine, so this will give you something different. And I'm going to show the chlorine molecule drawn out with its bond because we are going to break that bond. This reaction, very much like the addition of HX or anything like that we've already seen, the double bond attacks one of the chlorine atoms in the Cl2 molecule and breaks the chlorine-chlorine bond, and that forms an intermediate, not like what you would expect. It's a 3-atom cyclic, I guess it's not really a circle, triangle-ish intermediate. It's called the chloronium ion or the bromonium ion if it's a bromine atom. It's positive charge on that chlorine, and you see that both of the carbon atoms are bonding to the chlorine atom. These aren't full-on bonds. They're partial bonds, pseudo bonds. This is really unstable intermediate. The chlorine atom that we produced when we broke the chlorine-chlorine bond, the Cl-, that will come along and attack one of the carbon atoms in this intermediate. And it's going to attack from underneath, because obviously there's a lot of steric hindrance going on up here on top with this funky arrangement of the atoms. So the chlorine atom is going to come in down from below and hit that carbon atom and break the carbon-chlorine bond. And that's how we end up with the anti-arrangement of the halogens in this particular reaction. And it's just as likely that the chlorine will hit here as it will hit over on the other side and break the bond in the other direction. So we'll end up with both isomers. And that's an important thing to consider in this reaction. So let's look at a couple of examples of this in action. Let's consider this alkene. And let's use bromine this time. We'll go ahead and draw the mechanism again. So we make our bromonium ion in this case, and then our bromide ion is going to come in and attack from underneath the other bromine, and it doesn't matter which carbon we have it hit because it's going to end up hitting both. We don't really need to worry about which one we're drawing. And we have one bromine going up, and we have another bromine going down. Anti to each other. It's really important that we communicate stereochemistry with wedges and dashes so that there isn't any confusion. Drawing things in straight lines works really well when we're drawing out quickly mechanisms and things like that, but it is going to be important that we use wedges and dashes. So again, just like we saw with the halogenation, what we're going to do is pick two substituents that are on the same side of the original alkene. Like let's pick these two substituents over here. We could also choose to pick the hydrogen and the ethyl group if we wanted, but I'll just choose to pick the two methyl groups. And we're going to, in order to communicate the anti-addition, we're going to make them end up anti to each other in the final product. So we're going to say, let's make this methyl group a wedge, and we'll make this methyl group a dash, which makes the bromine a wedge and the other bromine a dash, and we've got our anti-addition. Plus we have the enantiomer of this molecule. And it looks like that. And you could also have done communicated the enantiomer by just writing plus enantiomer. Don't necessarily need to draw both of them out as long as you get one. Let's do one last example. I'll try to do this one without the mechanism. So in this reaction, let's just first rough it out, sketch it out like that. We're going to add two chlorines. They're going to go anti to each other. That's not communicating any stereochemistry at all. To communicate the stereochemistry, we're going to pick two functional groups that are on the same side of the original alkene. Let's go with a methyl and a hydrogen, and we're going to put them, they start out cis or syn to each other. We're going to put them anti to each other in the final product. So let's make this methyl group a wedge, and the hydrogen that's not visible, we'll make it a dash because we want them anti to each other. That lets us put the chlorines anti to each other. And the enantiomer. And you do need to double check and make sure when you're writing out that you're making enantiomers that you actually are making enantiomers. Maybe you're not. That's always a possibility. You can check that by assigning stereochemistry to both of the enantiomers and making sure that they don't represent the same molecule.